Yeah.
To recover.
There we go. It's on.
Okay.
On.
Okay, sorry.
Thank you. Okay, so we're going to start right away. I see Men-Andrin is there, so he's a star of the day. Good. But we're going to start first with Nolwenn and Rachel. So they give an update of their work. So Nolwenn, you're first. Is that okay?
Yeah, sure.
You can go ahead. Can you share the screen?
Not yet. It's not working.
Yeah, there you go. You should be able to. Yep, excellent.
Okay, so hi everyone. So I'm the project 6 and I'm working on the formation of the fold damage zones in carbonates and the link with the seismic cycle. Okay, sorry. Understand me. Just a quick reminder that the goal of my PhD is to understand the formation of fold damage zones, the factors controlling their spatial distribution, and their impact on the seismic cycle. So I'm going to show you the simulation I ran when I was in Munich. So I'm working on the fold Vado di Corno, which is in Italy. So here in Central Apennines near L'Aquila city. So just to see, like, Roma is here and L'Aquila town is here. And we are working on a straight fold because we started with like the most simple case. So here you can see the true shape of Vado di Corno. So it's like folding right here, and it's a normal fold. So there is many thrust fold that you can see in black, but we're gonna add it later to the model. So for the modelization, I'm using SEISO, which is an open source software for the simulation of seismic wave phenomena and earthquake dynamics. And sorry. So for the initial parameters, so we are under an Andersonian stress regime for normal faulting. And we can change SV, which is the maximal compressive stress vertical. And here is 1 because we are working on the normal faulting. SH, which is the max horizontal compressive stress. So I calculated and it was 140 degrees north. And the S2 ratio, so here is 0.5 because there is no strike slip component. It's like a real normal faulting. So for the velocity model, the velocity model used to compute the elastic and plastic properties of the medium, and on the next slide I will show you more about the one we choose. And we are using a slip weakening friction law with a static friction coefficient of 0.6, a dynamic friction coefficient of 0.2, and the critical slip distance of 0.4. And we choose these numbers because we found it in the literature, like they calculated from experiments. So we are using the velocity model of Ehrman in 2011. So it's the red line that you can see on the left picture. And we calculated rho, mu, and lambda from the velocity, VP and VS, sorry, velocity wave. So also we changed the air ratio. So air ratio is the relative press-stress ratio of potential dynamic stress drop to full frictional breakdown strength. It's the equation you can see on the right. And so it's between 0 and 1. And it tells us whether we're close to rupture or not. And if it's 1, the fault is critically loaded. And the larger is R, the higher are the initial shear stress, and the larger will be the earthquake. So for the plastic deformation, we use Drucker-Prager of full plasticity. And so the plastic parameter is constrained by the velocity model. And so we have the Drucker-Prager real criterion. You can see here, it depends on the plastic cohesion, mistress, and friction angle. And the plastic strain accumulates when the root of the second stress invariant is superior to the yield criterion, Drucker-Prager yield criterion. So first simulation we have is a simulation with a flat topography, so with this normal fault. So we modeled a box of 100 kilometers with a fault of 26 kilometers. And the fault mesh size was around 200 meters, and the box mesh size 10,000 meters. So we run our first simulation with an R of 0.7. So the picture you can see on the left is the rupture velocity at the last time step. Yeah.
Noel, can I stop you? Can you remind us again what R is exactly? Because
So R is the relative press-stress ratio. It's between 0 and 1, and 1 is like when the fault is critically loaded. So 0.7, the fault is like really loaded. So the larger is R, the higher the initial shear stress.
Because the denominator is basically the stress drop. Is that right?
Sorry, can you repeat?
So when I look at your definition, so what you have on the denominator is basically the stress drop. Is that right? I guess it is.
So the denominator is the straight drop. Yeah.
And what you have in a numerator is I don't know.
So like yeah, the stress drop and the strain drop.
Okay. Well, I need to think a bit more. So okay, go ahead, sorry.
So the rupture propagates, but so produces an earthquake too big because we wanted to model something near the reality. So at L'Aquila town, the last earthquakes was around 6 or 6.5. So 8 is too big. And I was saying that the picture on the left was the rupture velocity at the last time step. And so we can see here like the influence of the velocity model. It's like we can follow it. Okay, so for the plastic deformation, we put a bulk friction of 0.6, and for the plastic cohesion is dependent of mu. And we can see that the plastic deformation is mainly on the foot wall, and it's a bit turning, but actually I don't know why, but it will be more interesting with the topography. So for the topography, it's the same box with the same fold, but we add the topography. So the first simulation was with an R of 0.55, and the rupture does not propagate because the stress is height dependent, so the rupture doesn't go too far to the surface. And so we increased the R to have a rupture, so we got an R of 0.6. And the earthquake was still too big. We had a slip of 8 meters, which is too much. And I will show you really quickly, yes, the rupture propagation. Okay, just for you to see, have an idea. And so for the plastic deformation, for the plastic deformation of the simulation with the topography, we can see that there is more plastic deformation in the depression, so where the topography is lower. And we have the same shape here, so like this horizontal lines, the line that we had without the topography. And also most of the plastic deformation is in the footwall. So for the next step, we'll test the influence of the velocity model. So I will try to run simulation with other velocity model, test different values for the plastic cohesion and yield friction, and change the fold roughness. And also in July, I will go on field work. So I will try to use the models to get the field investigations. Thank you. Let's see.
Thanks, Nolan. Okay. Questions, anybody? Nolan?
Yes, I have one.
Yeah, go ahead.
Excuse me,
thank
who is
you,
talking?
Noel.
Because I cannot see.
Yeah, I don't know who's talking actually.
It's Erwan.
Oh, Erwan, okay, sorry.
I have my video on, but I don't know if you can see me or not.
Yeah, we can see you.
Yeah, okay.
I cannot.
So you start from an homogeneous elastic properties.
Yeah.
Once you have run a model, you get some change in the plasticity value. Could you iterate and introduce the output of the first model and use some of the damage that has been done in your model and put it as input in a second model to do kind of iteration, just to see how the plastic deformation is? Do you expect it to, if you have several earthquakes, it to wider or to go deeper? Well, what's your idea about that?
I guess we can do it, but actually I don't know how to do it, so I have to speak with.
And what would you expect if you run several times the model?
Like if I run the models with like the last output I had, like the output from the flat topography. I'm sorry, I'm not sure I understood well.
Without or any topography, but if you use the output of the first model as an input for a new model, and you do it several times, what do you expect in terms of the evolution of the plastic deformation zone?
Yeah, I think it's a good idea because in real life it's happening like that, like earthquakes are happening and there is already like damage zones. So I expect the damage zones to begin like to become like bigger and bigger, like to expand more, I guess, like in real life. So.
But in real life, I mean, it's not infinite, right?
No, it's not infinite for sure, but like the value near the fold will become higher, I guess.
Thank you.
Okay, Men-Andrin and then Ilona.
I think Ilona was first.
What was she? Okay, sorry. Go ahead.
I can go first if you want, man.
Go ahead.
So
Go ahead.
my question was about the cohesion, because obviously definitely very near to the surface, this value will have a big impact on how much plastic deformation you get. So I didn't fully get this, what mu means, and 0.001 mu. How much megapascal is that, and how did you choose this value?
So for the plastic cohesion for the measurement, I took like the value I found on the literature, and mu is the shear modulus, and yeah, wait.
And
someone say no.
No, it's 0.1 megapascal then, roughly, if I calculate very quickly. So that seems very low, I guess. But anyway, I mean, it's good to have input on that. And also with Maaike, she's also simulating the central Apennines. We were discussing an hour ago on the parameters in carbonites in the central Apennines, essentially. So maybe it would be nice to, together with Elisabeth, also make a collection.
She's working on the plastic deformation of the central Apennines?
I mean, we have plastic deformation in our model, but we don't necessarily focus on that. She's using a larger perspective, but we all need the parameters for carbonates.
Yeah.
So we need the viscous, elastic, and the plastic. And Elisabeth is working on the carbonate, so it might be an idea to together have a discussion on what parameters that we should use in these settings here.
Yeah.
And and check a bit with the cohesion, because this, I would say, this should be at least a few megapascal, up to a little bit larger there, and that will have a direct.
Okay.
But I saw you were testing the cohesion, so that's good.
Thank you.
Men-Andrin?
Yeah, super interesting. Really interesting what happens when the rupture approaches this surface. And I'm not sure we can ever answer this today, but generally I think it's interesting to just understand the overall first order shape of this off-fault damage. Like what makes the shape that you show in the slide? Is there sort of a qualitative way of understanding it?
The shape of the propagation of the damage? Is what you're saying?
Yes, and how it...
Yeah, for the moment we see that it's following the velocity models, but we have to play more with the parameters to understand better.
Okay,
Because the
thank
velocity
you.
model influence, but it's not controlling the plastic deformation. So
Yeah, you would expect where you have some free surface reflections, and maybe below that you would indeed generate some more plastic deformation there. So it's nice that you see that, but in your figure on the right, there's more plastic deformation also at a bit larger depth to the left of the fault. I must say I don't really understand.
So actually, yeah, we cannot compare like the model, the simulation with the topography and without, because it wasn't the same R. So also that's the reason why it's a bit wider for the sorry.
Yeah, so it's mainly the location at a the larger depth. You have more plastic deformation, but there
At the surface
higher because it's pressure dependent. So normally I would expect it more near the surface, as you nicely see in your other simulations.
Yeah, it's a
Maybe
bit
it has to do with some reflection to the surface, reflecting then again on your velocity profile going up.
And it's not normal because I mean there is something strange also, like it's a paper about it's Ma, and it's he is modeling the and we see that it's not, there is something similar here than what I have.
Yeah, but so here you do see it. Most of the other figures you do see it closest to.
It almost looks a bit as though topography is suppressing it, you know? I'm not sure from this perspective, but there seems to be the mountain to the left of that zone under which there's less.
Yes, it would be interesting indeed to look at the wave propagation. Maybe that's tuned to go in a different direction or something due to the topography. I don't know, but it's good to look at the waves propagating as well in the movies, right? And then get the feeling of where do these waves propagate, and what does that do to the plastic deformation?
Yeah, sure.
Super interesting.
Yeah, very nice.
Yeah, actually, thank you, Nolan, for this presentation. We were just discussing a few minutes ago before this, so these are really very, very preliminary. And just to say a few words, so Mathilde really made a great job to help her and to run it, because it took time. What really surprised me was the fact that it looks like, because of this reflection probably, which is very difficult for me to understand, topography plays a role. It looks sort of whatever this red thing is, it looks like it's far away from the fault. You see, it's more to the in the footwall. And the other thing is which is also interesting, but this is consistent with the more simple models by Ma, is that most of the damage is in the hanging wall, which is something already. So I think Nolwenn is in the good direction, but there are some issues in the direct comparison of the two models, topography and without topography, for a flat fault with the same deep angle. So this is something I think she will dig on in the next weeks.
If you really want to understand the topography, maybe you can even do intermediate models with slightly simpler topography. But that depends on whether topography is an important topic.
Yeah,
for
I
you.
think the idea was, we have this case.
Simplify the
Intermediate.
topography.
Like smooth it a bit.
Yeah, smooth it or tilt it in one direction, a flat plane, or it depends on what you are interested to find out. But there's intermediate steps between the fully flat and what you show here.
Sure.
Okay, we need to move on. Very, very good, Nolwenn. Thank you.
Thank you, Nolan.
Okay, Rachel, you're next.
Yep. Hi. Okay, so you should see the screen, right? Can you see the presentation?
Yes.
So just to kind of remind you of what I'm working on at the moment, part that I'm working on focuses on trying to reproduce the pulse variabilities that are observed in nature. So this was done by the GFZ group in Potsdam, where what we're looking at on the left is observed data. And in these plots, what we're seeing, so it's data on each station, the numbers are the station numbers. The size of the circle represents the amplitude of the pulse, so sort of the pulse PGV. The colors correspond to the period of the pulse, and the lines within the circles are showing the orientation of that pulse. And what this group showed, this is from one of the papers, a smooth model of the Turkey event that was published shortly after the earthquake. And in this smoother model, we can see that the variability actually observed isn't really being reproduced. So my goal is to try and see what I can add to this smooth model to try and capture this variability. So for the time being, I've started off with fault roughness, as well as adding heterogeneous DC values, so the fracture energy, and also with a super shear initiation. So for the time being, I've just been changing the different initial conditions. So I created my own plot similar to what the GFZ group did. And what was just a funny observation was the fact that I was using the data produced by AFAD. They provided process data, whereas this group was using ESM data. And in the classification of a pulse process, using the AFAD process data actually resulted in a lack of a few stations. So in fact, these three are missing from my data, which is quite odd. And the issue is that I can't really find any documentation of how AFAD actually processed their data. So now I'm going to move on, and I will just use the same data that the GFZ used, as they define exactly how they processed everything. It was just a strange observation. So here I've now plotted my different simulations. So this is the observational data that we saw before. This is the smooth model. This is including roughness. And this is including heterogeneous DC along the fault. So once again, the size of the circle, the color, and the lines represent the same thing. So the amplitude, the pulse, period and the orientation. And on comparison between the observational data and the smooth model, we can see that there is some variation when it comes to the period, but the size of the pulse and the orientation of the pulse is still not quite there. Looking at the roughness, it's a bit strange. In fact, it seems to completely mute the period. It's really low values and completely loses that variability. And in DC, it's a bit better. The DC simulation tended to produce slightly larger amplitudes as well. And then I attempted to try show the differences in all of these simulations. So what we're looking at seems overwhelming at first, but each plot has the different station IDs, which are categorized from north to south as they go from left to right. And each symbol represents the different simulations. And now here I've also included the super shear initiation. So the light blue squares are the heterogeneous DC. The pink circles are the smooth but subshear. The pluses are those with a super shear initiation, and the blue are those with on-fault roughness. And so what we're seeing is basically the absolute values of the observational data minus the simulation values. So here we're looking at the period differences. This is the PGV, and this is the angle orientation difference. On looking at the period, it's not very easy to see which simulation tends to outperform the other. I would say that those with the least differences would be the super shear or the heterogeneous DC, but it is still a bit challenging to actually say definitively which one is better. When we're looking at the amplitudes, then I would say it's more of the smooth that seems to do the best. And when it comes to the angles, it's more or less the smooth or the super shear. And in fact, the goal is to try and extract some more quantitative values from these plots to try actually see proper differences. For example, my next step is to take the average values of each plot and then properly see which on average works best. And then I also try to plot these differences in a different way visually on the maps. So this is the differences in PGV for the heterogeneous DC, for on-fault roughness, the smooth and the super shear simulations. When the colors are closer to white colors, that's where there's a little difference. Onto the blue is implying that the difference means that the simulation was smaller, whereas more towards red-brown means that the simulation produced larger values, since it's observation minus simulation. And it seems that in general, most simulations produced larger values than observed, except for the roughness. And a similar plot then for the pulse values. And this time it's quite a mix, but they all seem to range more or less between the same values in differences, except super shear has much higher with 9, and on-fault roughness produces the least change when you see it this way. And that's pretty much it. So the next steps, like I said, is to extract some more quantitative values from these differences. I'm also going to be attending a workshop in Slovakia at the end of June. So the idea is to find a really good way to show these results. Since there are many variables, it's a bit challenging to actually pass the message along. And in the meantime, there are still some things that need to be arranged in the actual simulations. And once that is complete, the next step is to include VS30 models. And that's it.
Thanks a lot. So you're still exploring the models and how it behaves to changes. Good. I was wondering actually, so your fault roughness is like one realization of a fractal surface, is that right? Or something
Yeah.
like that? So
It's considered in each case that I'm considering, I'm sort of assuming it's the best case scenario of that adaptation, rather than exploring different types of roughness, for example.
okay, so you mean you test different outcomes of rough faults and or you just take the first that comes?
I'm assuming that what I'm using has already been considered as the best case scenario to use, rather than testing different roughnesses, because it would be a whole other thesis on its own.
Yeah, sure. Men-Andrin, you have a question?
Yeah, sort of on the similar lines, very interesting question. What causes this variability? But you could, in principle, just tune up the roughness and then get more variability from that.
Yes, in
So
principle.
I wonder how well by whatever other study has constrained this, how well constrained this is, because presumably the source roughness is a tricky thing to characterize.
Yeah, just from what I've seen so far, and for example, we're discussing a lot with the GFZ group as well. It doesn't seem like roughness might be the right thing, the right ingredient to change. I mean, especially when you see it in this comparison, it's quite clear that it doesn't really capture that variability, that everything's the same. So maybe spending time to tweak the roughness and find what sweet spot of roughness would produce it might not really be an effective use of, well, time in this case, since everything has its own expense, even simulation-wise, as in. So it seems like it's more like DC heterogeneities that might really have an impact rather than, or something else. Hopefully I will find out.
What about pre-stress? I mean, is that something that you explore as well? So you have heterogeneity in pre-stress, because what creates pulses is the fact that your rupture stops and go all the time. And this is because, you know, sometimes it does enter into, you know, strong asperity. So, you know, it takes time to break. And then when it breaks, it, you know, it's a pulse again and so on. So the pre-stress I don't know, just in intuition, but maybe I'm wrong, but I mean, pre-stress is variable along the fault and might you know, play a dominant role there.
In fact, it's also something that we eventually plan on testing out.
Yeah. That's a lot of variables. Yeah.
Indeed. And if there are any suggestions on how to make these plots any less terrifying, I'm open to suggestions.
I was going to actually suggest on this to not just look at residuals, but also at the correlation of, you know, you plot the observed value versus the predicted value. And then you would, for example, also see if you do better at large amplitudes than at low amplitudes. And it would be complementary maybe.
Okay, I'm not sure I fully understood.
So now you plot the observed minus the simulated value for each station, but you could also just plot the observed value at the station against the simulated value at the station. And then if they were, if the predictions were perfect, then they would all be in a one-to-one line, but
yeah,
they will not be. And so you see how and where you deviate and where you deviate more than in other cases.
I was considering that as well. And you would actually see if you're above or below the actual values.
Yep.
Okay, any other questions for Rachel? Okay, so we can stop, I guess. Thanks again.
Thank you.
All right, so Men-Andrin, your turn for an update on your work.
Such is my work, but I do work on the topic, fortunately. So
Okay.
let me share my
Uh,
presentation.
Okay, you can start whenever you're ready.
You see this in full screen mode?
Yep, we do see it.
I think I can also somehow make a pointer. Anybody can anybody tell me how I can go into laser pointer mode? It's just this one.
Should be on the bottom left. You should
Oh,
find,
this one.
yes.
Oh, thanks. Awesome. Thanks a lot. Okay. So I would like to talk about deep learning methods for earthquake detection and characterization. Very simply, the overview is going to be a very brief introduction to seismic monitoring. We're going to talk a bit more about that in Sicily in next week. And then about machine learning, and then of course, machine learning seismic monitoring. So seismicity, as you know, is the collection of all quakes that happen in some time and space window. And so here's the example of the Ridgecrest sequence that had the 6.4 foreshock and the 7.1 main shock in 2019 in the desert of Southern California. And so for each of these large and sometimes damaging quakes, there's countless smaller quakes. And so I want to start with the question, why do we care about these small quakes? I mean, they don't cause any damage. They're not directly hazard relevant. Why are we interested in seismicity?
So is that a question, Men-Andrin?
This is
Or...
a question to the students, yes.
Okay.
Okay.
I think Giulio can also answer if he knows the answer.
He's not a student. So anybody wants to try? Go ahead.
No takers? Maybe the question is too simple.
Yeah.
Well, seismicity, small quakes are obviously interesting because they highlight plate boundaries, active fault structures. They can be foreshocks, so they can be harbingers of something bigger to come. They follow certain empirical patterns that we can then use to estimate seismic hazard. So we can estimate the probability of large quakes, even if we haven't observed many of them yet. They contain information about the mechanical state of the crust. They can be used to map reservoir permeability enhancements, for example, geothermal reservoir and oil. There's a lot of reasons. I was hoping that every one of you would suggest one of those, but I'm probably just making things too simple. To study seismogenic processes, we make seismicity catalogs, which are essentially just lists of earthquakes, and then we can analyze them. So, for example, if we take a global earthquake catalog, then we see right away, as you all know, that we then see the plate boundaries. We see where the subducted plates go under the ocean, and we see, for example, in the Tohoku quake, all sorts of different processes like intraplate quakes, volcanic associated quakes, and so on. But of course, earthquake data don't come in the form of earthquake catalogs, but in the form of waveforms. And so the art of seismic monitoring is to turn continuous seismic waveforms into seismicity catalogs. Of course, we do also other things with the data, but this is what we do when we want to study seismicity. And here's a 12-hour seismogram from, again, the Ridgecrest quake in California. This is a mock-up of an old drum plot back from when we used to have analog seismographs that were recorded on a drum. And so the way to read this is that every line, this is, I think, half an hour. And then after half an hour, it starts again here. You see they have a bunch of foreshocks up here. And then somewhere here on the fourth line, you have the main shock. This is the magnitude 7 main shock. And then it just keeps going. And for a long time, we just have countless and countless quakes. We want to know and catalog all of them. And the trick is to define or to develop monitoring methods that can actually, every time when we as humans experts see, oh, here's a P wave, here's a P wave, here's an S wave, and so on, that would detect and list these quakes so we can use them for example, for tectonic studies. And so this is the data from a single station, and in reality, we have a network of stations, each of which just reports continuous seismograms, and then we have to first detect the quakes, or the quake signals rather, on each of these stations, and then also do what we call phase association to say which of these phases across the different stations of the network belong or were caused by the same earthquake. And in these dense sequences or in earthquake swarms, this can become very challenging. And so in fact, there's a whole workflow of tasks that we need to do to go from continuous time series of ground motion from a network to earthquake catalog. So we first may do some pre-processing, and then we do we'll call this signal detection rather than event detection. Then we have to do phase pick-in, saying when the phases actually begin, associate the phases across the different stations, compute the quake locations, and so on. And the point of today's talk is that almost every one of these steps has been improved in recent years substantially by machine learning methods. Here's a famous visualization of this from the Central Apennines, from the Amatrice Norcia sequence, where Musavi and Baroza show a standard catalog, every dot's a small quake, and using PhaseNet, a convolutional neural network detector, this is what it looks like. So we get orders of magnitudes more quakes than we used to in standard method catalogs that we can then use to get a better image of, for example, faulting processes or faults on structure. And so how can we do this with machine learning? To explain this or to discuss this, let's first look into machine learning in general. So what is machine learning? A lot of the recent advances in machine learning come from the field of computer vision. And you can start with the question, how do you teach a computer to recognize a cat? And there's various ways to do this. The people have been trying to do this since pretty much ever there have been computer. And you can, for example, try and write an equation that describes the cat. Or you could do template matching, where you just take a lot of images of cat and just sort of scan them over the image and see if you get a good correlation anywhere. But what happens if you then have yoga cat? And the cat could come in any sort of shape and size and color. In fact, visual recognition is very hard because of all this variation that you can have of one and the same object. So you could have, different perspectives, you can have different illumination, different scales, different deformation. The object could be hidden. There's a lot of intra-class variation, so different cats can look very different, and so on. So there's a lot of reasons why this is very difficult, and people before deep learning algorithms have been a thing, we're really struggling to make good object recognition algorithms. And this is where machine learning comes in. Machine learning, there's a lot of definitions, but here's one that I quite like. Machine learning is a class of powerful algorithms that can learn information directly from data without relying on a predetermined equation as a model. So we don't need an equation for the cat, but a machine learning algorithm can itself find out how to detect the cat if we show it enough example data. And then to go beyond classical machine learning, deep learning just uses deeper models with more layers, and it can work on raw input data directly rather than on data features. And I'll explain this in some detail just in a bit. So there has been for a long time now the image classification challenge, which is about computer vision. So they have, what you see in the background are images with objects in them. They have 1,000 different types of objects, and they have 1.4-ish million images of them. And the challenge is to write an algorithm that classifies these images into the 1,000 different classes effectively. What you see here is the progress of the best models over the years from 2010 until about 2015. This is an error rate. So how many images were misclassified. And you see how this dramatically went down, especially in 2012, when the first deep convolutional network trained with graphics processing units became a thing. Notably, in 2015, this margin or this error went below the error that you get when you and I do it. So this is when ResNet, a particular algorithm, a residual network, actually outperformed typical human classification. So today, and this is almost 10 years ago now, today, we make a lot more mistakes than an algorithm would at this task of object classification. Machine learning, there's a lot of different types. This is a slightly outdated already nomenclature. Today, we're mostly going to talk about supervised learning, where we can do classification and regression tasks with large labeled data set. There's also reinforcement learning, for example, used in robotics and in gaming. And then there's unsupervised learning, for example, for clustering algorithm. But a lot of the progress that is useful for earthquake science has come from supervised learning. Of course, not exclusively, but I'm mostly going to talk about supervised learning. And many of these algorithms, the vast majority, including ChatGPT, have at their basis an artificial neural network, which I'm going to try and explain a bit how it works. So let's say you want to make a prediction on, in this case, this is an example from deeplearning.ai. You want to predict how popular a good is that you want to produce. And so, you want to know how many people want to buy this thing that I produce. And you know that this will have something to do with the price that I'm asking for, maybe with the shipping costs, maybe with the marketing that I can do, or maybe with the materials that I use. So you know these things affect the demand, but you don't know how. Now the trick of the neural network is that you can fit a function that will allow you to make a prediction without actually understanding these explicit relations. A bit more formally, this looks like this. This is an artificial neural network that has an input layer, then it's a couple of neurons in what's called a hidden layer, a second hidden layer, and then an output layer. And so the input could, for example, be features of a seismogram. So it could be peak amplitudes of a seismogram or some frequency measures of the seismogram. And what we could want to know is, for example, the probability that the seismogram we gave to the network contains a P wave. Let me step one step ahead. I think I should have said this earlier. This could be relevant, for example, if you build an earthquake early warning system. So let's say you want to have a classifier that determines if an input signal is a P wave or just a noise signal. But in the early warning case, you only have maybe 3 seconds or so of the P wave. Now you need to determine, is this a quake? So we should send out an alert, or is it a car driving past my seismometer, and then we should better not send out an alert. The classic way to do this would be that you could do it, for example, with a linear classifier. So you could measure some features of the seismogram. So you could measure the peak acceleration, the maximum velocity. We could count the number of times the seismogram crosses the zero amplitude as a sort of frequency proxy. There's all sorts of features that you can compute on this, and maybe some of these features or the features together will tell you if this is a P wave or not. And so, for example, you can make a similar linear classifier that computes a value y as just a weighted sum of these different features, so peak acceleration, peak velocity, etc. And the question is, what are these weights, W1 to W7, so that you make the right prediction? So you could define a classification threshold that if y is larger than some threshold value y prime, then the input seismogram with which we computed the feature is a P wave, and if it's smaller than that, it's a noise signal. And you can find the threshold value y prime as well as all the 7 weights with some optimization method. And this works really well if you deal with a linear problem where the two classes separate linearly, so you can divide them with a linear line in whatever number of feature space that you have. But often our problems are not linear, and then this will not work very well. And this is where neural networks can excel. And now I have to go back to this thing before, because the reason neural networks are good here is because they're inherently nonlinear. So what happens in the neural network is that we compute some we feed it with some input values, and then these input values are propagated through the network. And at each so-called neuron or node of the network, what we do is the following, what's described here. So we compute a relatively simple mathematical operation and then just pass the value on to all of the neurons in the following layer. And the mathematical operation is a weighted sum. So again, like in the linear classifier, we have some weight from each of the connections to the previous neurons. 2 plus some bias term that is per not per connection, but per neuron actually. And then around this, we compute an activation function. So we just compute a weighted sum of all the inputs of, and then we do an activation function. The activation function is some nonlinear function. There's a couple of different ones that are commonly used. Here I just show the example of a sigmoid function that then maps whatever comes out of this weighted sum to some desired range, in this case of sigmoid, to a value between 0 and 1. And so you compute this at each of these neurons and they pass it on. Here you do the same, just with different weights. And at some point, you have an output layer that will just be one number. And that could be, for example, the probability that your P wave or that your input signal is a P wave. Here's a couple of different examples of commonly used activation functions that introduce this nonlinearity into the network. And so rectified linear units, for example, have a kink and they just go return the input value if the input value is larger than 0 and 0 if it's a negative input. And you want to use different ones in different contexts. Without this activation step, the whole network operation would be linear. So you could basically express this whole thing as one big linear algebra operations, but then you'd have the same limitation as with just a linear classifier. You could only map linear relations between inputs and outputs. And so back to our linear classifier example. Now the trick is we want to train this network to make the right predictions, right? So that we give it the features such as peak acceleration of a P wave that out here it says maybe 1 for this is a P wave, and that it says 0 probability it's a P wave if we give it anything else like a noise signal. And the trick of the neural networks is that you can empirically train them with large sets of labeled data. And so you just need a library of a lot of signals that are P waves and an equally large library of signals that are not P waves, that could be S waves or noise or something else, and optimize all the different weights that you have in the network so that at the end, the network does what we want it to do. And this can be done with optimization techniques such as stochastic gradient descent. And so when we give the network some input, it will produce some output that could be good or bad or anything in between. And this output is a function of all our weights in the network. Remember, every connection between neurons here has a scalar weight, and every layer has a bias. And so this prediction is a function of this of these parameters. And then we can compute a loss or a misfit function that measures the distance between the true label, so whether it is a P wave or it's not a P wave, and what the network predicted. So this loss can be, ideally, if the network always says the right thing, then this loss would be 0 in this case. But if we sometimes make mispredictions, then this loss becomes larger and larger, and so we want to modify the weights such that this loss becomes smaller. Exactly. So what we want to do is we want to find all the weights of the model, so these W's and the biases that minimize this cumulative loss function. Or in other words, we want to find the weights and the biases so that the predictions of the model that come out at the end best agree with the known ground truth, which is the true label, for example, that it is a P wave. And these type of networks are often called multi-layer perceptrons. How we get to these parameters that then make the network perform well is quite a field of study of its own. And so it's the field of parameter optimization. And because we have a large number of parameters, this is very high dimensional. So basically every parameter in this net, so every connection between neurons is its own dimension. And these networks can be very large. And so we have very high dimensional space. In 2-dimension, we can visualize this as such that we have some loss function that whereas as a function of 2 parameters, and now we need to find a way to go to the parameter combination where the loss is minimum. And in small enough problems, we can do this with grid search. We can just try out all the possible parameter combinations and then pick the one that results in the lowest loss or the lowest misfit. In real problems, however, this is often untractable. So neural networks can have millions or even much more free parameters. And so there's no way we can try out all the different combinations. In some cases, we have analytic solutions for the loss. For example, if the loss function is quadratic, then we can just compute derivatives of the loss function with respect to all the different parameters, and then do a targeted optimization. Or we can do this in a stochastic way, which is actually often more efficient, even if there is an analytical solution. And a recipe for this is, so the training recipe is that we start with some initial, for example, randomly drawn weights, and then we can compute the derivative of the loss function with respect to all of those weights, and then we know in which direction we have to change the weights so that we get the best loss reduction. And so we do this iteratively, which is we compute the derivative, we compute the loss function, then we compute the loss function derivative with respect to all the weights. We update each weight a bit in the direction of the negative gradient, so that next time we compute a lower loss, and we can just do this until the long loss no longer strongly decreases. Then we have to start worrying about overfit. So if we do this on any particular data set by construction, this loss will always go down because we just find out in which direction the loss function will be reduced. But at some point we start overfitting the model. We're saying that we don't learn any general property of the data anymore, but we just basically learn specific properties of the seismograms, for example, that we gave it to train this model. What we want to learn is only the general properties that if we have that we then go on to a new data set that the model then performs well. And to do this, we need to split the data set in at least 3 subsets: a training data set, a validation, and a test data set. And so we use the largest part of the data usually as training for updating the parameters in this iterative way that I described earlier. Then we use the same model and use it on a data set that has not yet been used. And so that's the validation model. And when we start overfitting, then the loss in the validation model actually starts going up again, because now we're doing this overfit thing. We're no longer learning anything general. And so we know this from the validation model that we need to select this model, that this is the best and most general model. And then we have kept back another set of the model, which we call the test data, on which we can then evaluate the model independently of any data that the model has seen so far. I haven't said how we compute actually these updates. Like, how do we actually compute the derivative of the loss function with respect to the weights? And this is maybe a bit of a complex concept to wrap one's head around. So we have some input and some output, and in between a lot of weights. At the end of the day, the math is actually surprisingly simple in that it's just a repeated application of the chain rule that we can just back propagate the derivative of the loss function with respect to every one of the model parameters. This is something that we can that is surprisingly easy to do because we can just compute the local gradients at each point in the network and then multiply the local gradients with each other. But If you're interested in this, we can talk more about this in Sicily. There's some very instructive examples for how to do this, but at this point, I guess this is too much detail. So as a summary of this general artificial neural network concept, neural networks are networks of relatively simple operations. So at every neuron, we do something very similar, mathematically simple, but together they constitute this very complex nonlinear mapping function. And we can train these networks with large amounts of labeled data, so we can empirically optimize all the free parameters, namely the weights and biases. And in this process, we can design very generic systems that are capable of discovering complex and importantly, nonlinear relationships between some input feature and some output values. And the example that we've seen is the seismo example, that features computed on a seismogram, and we want to predict if the seismogram is a P wave or not. So I think I already said all this, and maybe skip this. And so here's a cartoon that I like. So this is one guy that is not impressed with the machine learning algorithm, or the other guy said, "This is your machine learning system." So yeah, you just pour in the data into this big pile of linear algebra and then collect the answers on the other side. And what if the answers are wrong? Well, then you just stir the pile until they start looking right. And so in a sense, this is not very far from the truth, except that we don't just stir the pile randomly, but there's these targeted optimization algorithms that let us find the weights that we need for the answers to become the right ones. Okay, so that's sort of a general intro to artificial neural networks. Now, how can you use these for seismic monitoring? And to do this, we need to introduce one more important concept, and that are convolutional neural networks that are at the heart of many of the very powerful algorithms that we have been using and that we keep developing as a community in the past almost 10 years now. I'm then going to show in some detail the example of face detection and characterization, but also briefly summarize some other applications and the science potential of this all. So convolutional neural networks, or ConvNets, have been really a game changer for quake monitoring. So I already showed the Central Apennines example with the PhaseNet algorithm. That's a convolutional neural network phase detector. Another example that I'm briefly going to be showing is a fully convolutional signal denoiser that you can train to separate in some input waveform the noise from the data. Convolutional neural networks can be used for all sorts of fun things, like changing the style or merging the styles of a picture. For example, the photo of something with some artistic style, and so you can make your San Francisco picture look like have a bit of a Van Gogh vibe. And the general principle of convolutional neural networks is as follows. So the classic ConvNet combines the neural network as we just described it, that is shown here in the last two layers of this network, with what we call convolutional layers. And the convolutional layers are these with the larger symbols, and they contain or consist of numerous parallel but also sequential digital filters. And so these filters transform some raw input data, for example, a bitmap image or a seismic waveform, into a feature vector. And it's this feature vector that is then fed into the standard neural network that makes, for example, in this case, an image classification. And so this is an algorithm from computer vision that would take a photograph of something and classify if there's a dog, a cat, a boat, or a bird in this picture. And so what is this convolution operation that is happening in these convolutional layers? A convolution is a mathematical operation that folds, we say, an input vector x with the convolution vector. And so if you write this out in terms of the components, so you have a vector x, naught until x5, and you convolve with an operator h naught h1 h2, you get some other output vector that is just, this is basically a sliding operator that we slide over this input vector. And so, for example, if we have if all the h vector component were 1/3, then this would just be a moving average. So at every point, we would just compute the average between 3 consecutive samples and then move on. So this would be a moving average filter. If you write this in matrix notation, it would look like this. So it would be a sparse matrix with only the 3 near diagonal components being non-zero. Importantly, convolution is a linear and differentiable operation. And this is important because only then can we actually do the backward propagation of errors to actually do the parameter updates with stochastic gradient descent. And now this can also be done in 2D. In 2D, instead of just moving this filter over a time series, you can actually slide it over a picture, and the definition of the thing of the operation is basically the same, just you have an additional dimension. Depending on how you choose these filters, so your H, you can get different effects. So if your H matrix is a 3x3 matrix and only the central element is non-zero, then you just get an identity filter and the output image will be the same as the input image. You could also, for example, do edge detection filters that highlight differences in your bitmap image. You can have a sharpen operation filter. You can have something that blurs the filter. You can really design this filter to change the image in a desired way. Now, the trick of the convolutional neural networks is that we don't have to design these filters, but that these filter coefficients are the thing that the network learns from the example data. So we don't have to say, what filter do you need to apply to the seismogram so that you can tell whether or not it's a P wave or an S wave. It can learn this from the data itself. And I think this is the key power, or one of the key elements on why these algorithms work so well. Just to mention, this can also be done in 3D. So we're not limited to 1 or 2D. This equally works well in 3 components. And so, for example, a bitmap image consists of 3 color channels where you have the 2 spatial dimensions and then red, green, and blue. In a seismogram case, this could be the 3 spatial components. And so the filter H that we had introduced earlier is just a vector of scalar coefficients. And these are the coefficients that are optimized during the training, just like we had in the convolution, in the standard neural network. We had the weights between the different neurons, and now we're also on top of that optimizing the filter coefficients. So what this algorithm then does is it just turns the raw input data it filters it sequentially, but also in parallel. You have multiple channels in parallel into something that can then lead to a very good classification in the end. And so this is, you can think of these first convolutional layers as sort of an automated feature extraction system, so that you no longer have to decide yourself, well, what features in the seismogram, say, are relevant to see if that's a P wave or noise. You can just let the machine learning algorithm figure that out by itself. Another step that I haven't introduced yet is pooling. So you see how we go from these large matrices to the smaller matrices. This is done by pooling. For example, this is very simple. For example, you do max pooling, where you just take the maximum in 4 consecutive samples. So this would be 6 in this case and 8 here. And so you get a smaller representation of this data. And so you do this, and then you continue on the smaller scale, and you keep doing this until you have very small matrices. And one effect of this is that you can then detect things in a scale invariant way. So you can detect, for example, you have an image of this. You can then detect an object, for example, a person, whether it's in the foreground or in the background, or you can detect a P wave, whether it's tiny or whether it's very large. So that's why we do pooling. And so I showed this ImageNet challenge in the beginning, and the this 2012 model AlexNet was really a breakthrough that resulted in a performance leap in this image classification task. And since then, a lot of the models that have been performing really well have convolutional elements in their models. Okay, so now finally that we know a bit what the conv nets are, we can start talking about actual seismic problems. So seismometers record quakes, but also a lot of other stuff. So for every quake there is on a typical seismometer, there's also a lot of noise data, for example, from traffic, from weather, from all sorts of sources. And so just like we want to say, well, is this a boat or a cat? We want to say, is this input seismogram a P wave or an S wave or noise? And this is actually one of the first things that we had done. But instead of the image input, we now have just a seismogram as an input. I said earlier, the RGB image has 3 color channels. We have 3 spatial channels, but we can do almost exactly the same thing. You can just basically take a visual recognition algorithm and change it very slightly, and then you get a seismogram classification algorithm. And you do these parallel filters to sequential filters. You at the end write it all into one large vector. You put that into a fully connected neural network, and then you can get, in our case, with the 3 probabilities that sum up to 1, the probability that the input is a P wave, an S wave, or noise. And the way we've done this, I'm going to skip most of the details here, but the reason why we can do this is because in seismology, we have an almost outrageous amount of hand-labeled data. So for example, at the Southern California Seismic Network, we have over 20 million hand-picked P and S arrival times. So there's people that just do, for the most part of the day, nothing else than just go through seismogram and say, well, this is a P wave, and here's exactly where it starts. This is an S wave, and here's exactly where it starts. And then they also pick first motion polarities. They say, does the first motion first go up, or does the first motion go down, or maybe I can't tell. And then we label it as undecidable. Because we have these large amounts of data, we can train these large neural networks. And this is why this works so well. So in this case, we had taken for P waves, for S wave, and for noise, we've taken 1.5 million 3-component seismograms each. And this is a data set, by the way, that is available on the Southern California Earthquake Data Center webpage, readily available to train machine learning models. And then we train this on graphics processing unit. And what you can end up with is a classifier that when you give it a signal, you can just go in sliding windows over an input seismogram. And red is here the P wave probability. So as soon as the P wave comes, this probability goes up. And then later the S wave comes in, and then the S wave probability goes up. So here you've seen, okay, I've detected P and an S wave. That's probably an earthquake signal. We apply this to a seismic sequence near the Salton Sea, near the Mexican border. This is the beginning of the San Andreas Fault. And so whenever there's a sequence down here, people in California get nervous because this is one of the scenarios of how the big one on the San Andreas Fault might one day start. And here's how this then looks on data, on continuous data. You have a lot of quakes that come in close succession to each other. And we always detect the P in red and the S waves in blue. And we zoom in a little bit, and you can really see that these signals are very close to the noise level, and they overlap a lot. And standard pickers like short-term average, long-term average pickers would not detect most of these. Maybe they would trigger on some of the S phases, but they would never be able to detect most of these, and especially not with the P and with the S phase. And so in this case, we detected something like 8.3 times as many events as in the was in the Southern California Seismic Network catalog. Now, this is maybe the most prominent example of how to use ConvNet in seismology, but we can do a lot of other stuff with this as well. So we can take this network and just change it very slightly, and actually train it into a first motion polarity picker. And then the probability is no longer the probability that the input seismogram is a P wave, an S wave, or noise, but whether or not the first motion is up, down, or unknown. So we can take almost the exactly same algorithm to do quite a different task. And I think this is also one of the core strengths of these types of algorithms, that they're so flexible and applicable to different problems. And so this network had a couple of convolutional layers and then fully connected layers. More recently, people have started doing fully convolutional networks where you have first these are so-called unit architectures where you do the convolution and the pooling, convolution pooling, but then you do extension again, where you basically do the opposite of pooling, but again with convolutions, and then you end up with something that has, for example, the same dimensions as your input image. An example of this is PhaseNet that was used in this central Apennine seismicity example that I showed initially. And then instead of just with like a scalar prediction, you can end up with actually a vector prediction of where your P wave is. And you can say, you can get sort of like a triangle or a bell curve that tells you, well, somewhere here is your P wave, and somewhere here is your S wave. Something very fundamental in machine learning has been the invention of transformer, developed by the Google group. And this was the underlying breakthrough that ultimately enabled things like GPT models. They also involve a lot of, so this is not cheap, this is a earthquake transformer by Musavi et al., which does signal detection, P phase picking, and S phase picking simultaneously. So it's sort of a multitask model that first has an encoding part and then splits it up into 3 different tasks. But what makes it a transformer is the self-attention mechanism that is, in a way, a bit of a way for the network to learn where it needs to pay attention to, so that when it wants to say, where's the P wave pick, then it has learned that it needs to focus on this part of the signal, whereas when it's the task to do the S wave picking, then it knows it needs to pay attention somewhere else. And these type of models, they just turn out to get better and better the more data we throw at them. And so a lot of machine learning these days involves just getting bigger computers, bigger data sets, and then your model of the same type, same architecture, ends up performing better. One thing that I find really intriguing and fun is signal denoising. It's quite marvelous that this works. And this is from a recent paper by Nico Dahmen, who just recently did his PhD at ETH. And he developed, based on a similar algorithm that came from the Stanford group, a denoiser of InSight data from the InSight NASA mission, where they placed a seismometer on Mars. And so the idea here is that you can try and take a noisy signal, transform it such that you end up with a separate time series for noise and one for signal, so that you'd have a cleaned out signal that is no longer contaminated by noise. And what you can do is you can do a short-term Fourier transform. So you compute a spectrogram for your 3-component input data. That means you get 6 matrices for the 3 components, and for the real part and the imaginary part that you get from the short-term Fourier transform. And then you can use a unit architecture to predict what are called segmentation masks. And these are just matrices of the same dimensions as your input spectrogram, and they have values between 0 and 1. And 1 means, okay, if in the noise segmentation mask, If it's 1, it means this frequency time combination is all noise. If it's close to 0, then it's maybe signal. And so correspondingly, the signal or event mask would have a high value here and say, well, this frequency and time combination, a lot of this is signal. So you take an input signal, you compute the short-term Fourier transform, you feed it through the neural network, and then you get these segmentation masks. Then you can take these segmentation masks, multiply them with the input signals. So these guys are the same. You just multiply them, and what you get is the short-term Fourier transform of the noise and of the signal or event. And then you can do the inverse short-term Fourier transform, and you end up with just noise and just signals. And so what sounds a bit like magic actually demonstrably works really well. And under a lot of noise conditions, you can effectively take out the noise from seismic waveforms. Another really interesting thing that is also becoming more and more relevant is signal synthesis. So with generative models, we can produce synthetic images. So this is from a webpage. You can try it out. thispersondoesnotexist.com. Every time you click it, you get a portrait image of some person that is completely made up. And they not always, but often look very realistic. This is based on an algorithm called StyleGAN. And something that we've been working on is this, instead of this person does not exist, this quake does not exist, a way to create synthetic seismograms conditional on some input parameters like magnitude and distance. So we're working on creating a way of creating stochastic seismograms that we could then, for example, use in engineering applications when we test what sort of ground motion a building could withstand. So to summarize the methods part, the artificial neural networks are networks of simple operations which together constitute nonlinear mapping functions. These mapping functions are generic systems that can discover complex nonlinear relationships between input features like a seismogram and output values, like the probability that the input waveform is a P-wave. And in seismology, they can be used for a wide range of tasks, including phase detection, association. I didn't talk about phase association, but that's another common application. We can use it for signal denoising, we can use it for signal synthesis, and really much more. And the promise of this is that with these deep learning based monitoring tools, we can now have substantially better data products such as seismicity catalogs, which then in turn can help us understand seismogenic processes. And just as a sort of final part, one particular application that I find particularly promising. So here's a deep learning generated seismicity catalog from what's called the Cahuilla swarm, which is a swarm in Southern California, where they've used a deep learning method. And you see, so this is a map view of a dipping structure. You can see as it gets darker, it gets deeper. So this is a steeple dipping structure. You can see all this, these shapes and streaks in here. We now, because we have this enhanced sensitivity, we're able to really to see how the structure looks in 3D. So if you take cuts in dip or in strike direction, then you can see the actual 3D shape of this underground structure that would otherwise be completely unknowable. And so, for example, with the SciSol models that we've seen presented earlier, now you actually have a way potentially to measure the roughness and the non-planarity of this structure, even though it's at large depths and completely inaccessible. Similar thing we do in the Pedretto lab, which I'm probably going to talk about in Sicily a bit, that we have some seismicity clusters at depth, and we have enough resolution that if we do this slicing operation, we can see the intricate details of this zone in 3D. Yeah, that's it. So the hope is that these new methods will provide a better understanding of seismogenic processes through an observed and improved observational basis for our studies. Thank you very much.
Thanks a lot, Men-Andrin. A very very stimulating presentation.
Yep.
Okay, we have time for questions. So, students, that's your time to ask questions. Well, I'm going to start just to break the ice. What about false detections? So I guess I mean, when you detect, like, millions of earthquakes, like, at small magnitudes, there's a lot of not real earthquakes in a data set. So how do you deal with this? I mean, so there's a threshold somewhere, that you adjust, and how do how can you tell, whether you detect, false, earthquakes?
Yeah, this is very important. So thanks for bringing this up. For example, in the Central Apennines case, we have what Yenjo Tan and colleagues did. They detected 15 million seismic phases, PNS phases, and so it's obviously not possible to go through these by hand. And so you can do at least two things. One is that you use the labeled training data set or the test data set to see how often you made false positive detections. So you said P wave when in fact it was noise, or when you had false negatives when you should have said P wave, but you said noise. And on the test data, because you have the labels, you can actually compute this. And so what you do is basically you can do in our case, we had over 1 million test records that we hadn't used, that the model hadn't seen. And you can then define precision and recall, which is inversely proportional to the number of false positives and false negatives. And they trade off with each other. So, and then you can see the combinations that you can get between precision. So a precise model is one that never makes a false positive, a false prediction. And a model with high recall is one that never misses a phase. And so you can see the sort of combinations that you can get. And in this particular case, we're sort of in the, 99.5% precise and 98% recall. So you have an idea of how often you fail. When you then go to an application case where you don't have the labeled data, then you can't do this and you don't really know. And then it's important to just look at a lot of data. And I would usually just visualize a lot of the data and then see if I agree with what the network decided or what the algorithm decided. And so I would make these overview plots with a lot of predictions on it. And then you quickly get a feeling for whether you're wrong 10% of the time, 1% of the time, or 0.1% of the time. And if you have a good algorithm, then fortunately these numbers are often rather low. And for example, in the Amatrice case, it was really difficult to find errors at all.
Really, yeah.
But it is super important to not just trust that the model does the right thing, because before the model is good, often it does screw up.
Okay, so since nobody's ready to ask more questions, I have several, but I mean, it's not, I just ask another one. Just so you presented the stuff on the denoising. So just wondering, so what will that improve in the end? You believe this will make the arrival time, better constrained, or the polarities will be improved, or, what will you get from this mainly, according to you?
Probably both those things and better detection. So if you have lower noise, because in denoise it, you detect also more of the weaker phases. And this is something we're currently trying out. What Nico Damon's shown on the Mars data, so he was able to increase the seismicity catalog by 60%. So the model detected all of the quakes that were already known, sort of on the order, I think, of 1,000, and then on top of that, 60% more. And then you can potentially get better phase arrival time estimates and better polarity classifications. Now, obviously, everybody's super skeptical and says, well, but you don't really know what comes out of this machine learning algorithm, and so it could distort the waveforms in any which way, and so you get wrong estimates from that. But then Nico Daman actually showed that the distortion of the waveform from this denoising algorithm is smaller, substantially smaller than that of a Butterworth filter, which everybody uses, and we always use and just apply to the data without thinking too much about it. And so I think there is at least a potential that this can be used for better phase arrival times and polarity estimates and other characterizations as well.
Very good. Maybe Aurora first and then one. Yeah.
Oh, I was just wondering if algorithms which tackle different problems at the same time exist, and if they exist, if they are more or less effective. We were talking about phase picking and then denoising and then polarity identification. I was just wondering if there could be something that could do everything together, or if it doesn't make sense and it would be better to just like proceed in different steps.
So beyond geophysics and earthquake seismology, this is definitely a big trend that people try to develop these general models and multitask models. In seismology, there's a small numbers of those already, so that like earthquake transformer that can do 2 or 3 relatively similar tasks. I haven't seen yet sort of a comparison between a model that does multiple tasks and then compared to dedicated models for each individual tasks. But in other fields, notably in data science itself, it's become quite common. So that, for example, the GPT models, they can do a wide range of tasks simultaneously and can do them very well. And yeah, so this will be an interesting thing for the study. I'm sure people are working on this.
Alexander.
Yeah, I was wondering, you talked about how there are similarities between the image processing or the analysis and the seismological applications, and of course FaceNet is based on UNet and so forth. Is the denoising, how similar is the denoising in the seismological context to like image denoising, well, not algorithms, but machine learning applications for photography and so on?
Again, they're very similar. So the original algorithm is from Ronneberger et al. And I think, I haven't looked at it in a while, but I think it's some image processing technique. And then the Stanford group took this and made Deep Denoiser, which has largely the same architecture with the change that you use it for, well, they actually used it on spectrograms rather than seismograms. So it's very similar. And a lot of these things are not, we don't have to start from scratch, but we usually go and see what's out there in a similar problem, and then you get their code and modify it to your needs. So
Okay.
in a lot of these problems, and now in this signal synthesis case, we use a lot of algorithms from audio processing, because again, that's very related. It's just a time series of amplitudes. And so we can actually build on existing models. And it's also one of the really cool things in the data science community. That's very common practice to share codes, share data sets, so that you can actually go and build on that.
Okay, thank you.
John, do you have a question?
Yeah, just a small one. Can you hear me?
Yeah.
Yeah.
Okay. I just have one question. It is possible to train an algorithm that detects something that you didn't know. Such as, I don't know, if you try to well, if in the beginning you don't know about, I don't know, the hanging wall effect, but you try to put like a lot of data into the model, it is possible that it will highlight something that you said, oh, okay, I need to have a look on this one, and and this kind of stuff? It is possible?
Yes, but with different methods. So the supervised learning algorithms, they just sort of rely on that you provide a lot of examples from all the classes that you could potentially care about. And it will interpret all the data you give it in that context. And if you give it signals that are not represented in the training data set, then it can just become a random prediction. It will never give you a class for which you didn't train it. But in unsupervised learning algorithms, there's actually some very cool recent work from people in Grenoble, Steidou and colleagues that that use unsupervised clustering algorithms that would just classify all different types of signals that you have, and in a relatively interpretable way, so that you can then go in and see, okay, here I have these 12 dominant signal types, and type 3 occurred here, 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 and here, and then you can visualize them and you see, oh, this is actually wind noise, or this is actually some process that you in your hanging or footwall that you may care about. So there are methods, but they're not the supervised type methods.
Okay, thank you.
Do you have a particular problem in mind that you would like to that you started with this?
No, okay.
Okay.
Yeah, unsupervised learning is cool for exploring new data sets. Okay, yeah, Erwan, yeah.
Just okay, just a quick one. It's about the denoising things. I was wondering, for the learning part of this method, do you need to learn the noise and the events you want to detect, or can you simply have some sample of the noise and say, okay, this is noise, but I don't know exactly the events? How does it work, the training for the denoising?
Yeah, you need to show examples of where you know which one's noise and which one's which part is signal. And one way to do this is just to use synthetic signals, or you can use signals that have very high signal noise ratios and then contaminate them with noise. And so you take a signal that's very well recorded, you add a lot of noise to it, then it's no longer so well recorded, and then you can say, now here's the noise, here's the signal, here's the combination, now take out the noise.
Okay, so you cannot just say, okay, this is noise with something else I don't know very well, and extract me what is behind the noise. No, it's
no,
not,
unfortunately not.
Yeah.
I guess it depends on the spectral content in any case.
Yeah, if they're very well separated in the time frequency domain, then you can probably also separate it with simpler methods. But usually have overlap of the noise and the signal frequencies, and then it becomes more complicated.
Okay, thanks.
So last question for you, Men-Andrin. Will deep learning be able to predict earthquakes, according to you?
I skipped that slide. So there's a lot of people before the deep learning revolution, as we call it, has happened. Earthquake prediction was sometimes referred to as the P word, because it's been misused so many times that people didn't want to talk about it anymore. It was considered unserious. And then when machine learning became a thing, people started realizing that with random forests, they can, in lab quakes, predict the time until the next failure of some sample. And then it kind of became a science topic again, and some people think that this will happen. I personally am not holding my breath. I think the lab results may not be representative, and some lab colleagues of mine tell me that it may just be the lab machine that starts quaking as you approach failure with higher stresses, which is not something that you would observe in real quakes, but also I'm in no way an expert in this, and so it's an interesting. I wouldn't rule it out, but I'm also not holding my breath.
Better not. Okay, good. So maybe we can call it today, if that's okay with everybody. Thanks a lot again, Men-Andrin. Very nice presentation.
Thanks a lot, everybody, for
and so we again in 4 weeks' time with Bruno, actually. But you have the Sicily school before, so enjoy that one. Go easy on the wine. Sicilian wine is quite heavy. All right, so see you everybody.
Thanks
Ciao,
to you.
everybody.
Ciao.
Thank you. Goodbye.
Bye bye.